We are in session 3. So, as Ron pointed out, after an hour, we will be at the midpoint. So we've moved past kind of basic foundation concepts, and we've moved into the phase where we're going to start building models. And we'll build models incrementally over the next 2 weeks. Today we're going to go over the unconditional means and unconditional growth models and look at and talk about ways to look at the variance components as a way to see how you are improving your model and where the unexplained variance is and so forth. Careful. So, one question I had is, what should we do with session 6? And my proposal is to talk about GE. We could leave it open to see, what do we need to do for odds and ends as far as the MLM portion of the courses. I do tend to plan it that we cover everything, so you guys would need to come up with the MLM topics that we would cover in that final session. We can talk about power in MLM. I don't know that would take a whole session, though. So what's the interest in going over GE?
I'm interested.
Yeah, show of hands? So that looks like a majority. Okay. And are there other suggestions for the final session?
We can go into a little bit more detail about EMA and how MLM would apply to EMA measurements.
Yes, and in fact, I could probably try to incorporate that in 4 and 5. I'm not an EMA researcher, but I certainly can think about it and look into it. Yeah, I think it's a great suggestion, very applicable to a lot of folks. So I'll think about that more. Maybe I'll think about a part-time guest speaker, like a half-time guest speaker, even an EMA person. Yeah. Other suggestions? No? Okay. All right, so starting with a review. Looking at just thinking about a typical multi-level model. The overview is that we have the level 1 submodel, which is comprised of an individual growth model with intercepts and slopes plus the error. There's the level 2 submodel, which is fixed effects for between person effects on these random intercepts and slopes. So it's the 2 subsequent equations that predict those 2 level 1 growth parameters. And then we have the level 1 and level 2 specification of the MLM, which has separate equations for intercepts and slopes. That's what I just said. Composite model, which combines the level 2 and level 1 models into a single equation for hypothesis testing. And all of these models have both structural components, which we're thinking about model coefficients, and stochastic components, and that's where we're thinking about random error terms. So the best way to do an MLM is to do it incrementally in steps, so that you can look at the way the model, the way the variance explained, and the residual variances change as you add subsequent predictors. So first you fit an individual growth model, and then you model predictors of those parameters when we're thinking about longitudinal data analysis. At each step we can examine fit statistics or deviance statistics and variance components and changes in variance components. And the changes in variance components is what we're going to talk about today. And then we'll talk about the fit statistics next week. So step 1 is the unconditional mean model, where participants only vary on their intercepts. Step 2 is the unconditional growth model that adds the linear effect of time. I always kind of default to linear. I think it's next week we're going to talk a lot more about playing around with time, and so we'll get into other ways to think about time at that point. Step 3 is that we fit models that maybe control for certain covariates and or test for certain between person effects. So we might have control variables at level 1 or level 2. We may have substantive variables of interest at level 1 or level 2. Typically, we think about substantive variables of interest at level 2. But it's not necessary, particularly in a, say, for example, an EMA study. What's the goal? Like I said, to see how we improve the model at each subsequent step. So the way we're going to do it today is the way we do it every week, which will start with like the Singer and Willett type examples that go through the equations and their conceptual example, and then we'll move into the Chris Kaler example, which is the smoking treatment study, and that includes the syntax and the output and so forth. In terms of reading for this week, the Chris Kaler, the paper that this is the later portion of the course, or the later portion of the session is based on, is in there if you want, like, you know, spoiler alert, because you'll find out what he did with time, or what we'll talk about in terms of time, probably next week. Singer Proc Mixed is a super accessible, helpful paper for doing MLM and SAS. And then I put in a couple of, I think at least 1 or 2 PowerPoints for MLM in M+, or at the very least latent growth curve modeling in M+. And we're going to talk about that a little bit more, or more at the end of the session. Yeah, that's it. Okay, so, all right, step 1, unconditional means model, right? We've got the, let's see if I can use the, no, okay. We've got the level 1 model, which in this case is the Singer and Willett example of adolescent alcohol use just over the course of adolescence, so it's ages 13 to 17. So in the level 1 model, we're predicting alcohol use over individuals and time, right? That's our I and J, as predicted by the intercept within person plus the incremental error due to within person and within person variance, both due to I and due to J, so due to time. At the level 2 model, we have that individually varying intercept predicted by gram mean plus the error between persons, right? So here we see our within person error term is on the top, between person error term is here. In the composite model, we've got all pieces combined. So the composite model tells us that adolescent, what is the prediction of adolescent alcohol use over ages 13 to 17 as predicted by average initial status in alcohol use, and this is centered at age 13. In all the Singer and Willett examples, they're centered. Plus the between person differences in intercepts, plus the within person residual variance due to person and time. So that's what all this stuff says. And then you can trace the equation down to the output, and this is output as you would see it like in a paper. So we've got the fixed effects initial status, which is here, so this is the intercept, right? So the starting place at age 13 for alcohol use. And then the 2 variance components for this level 1, for this unconditional means model. So the within person variance, 0.562, and the between person variance, 0.564, okay? So this is what you were talking about last week in terms of running the unconditional means model to get a sense of the proportion of between to within person variance. And you can, calculate the ICC either way depending on which one you're more interested in. I mean, they're opposite sides of the same coin. So, any questions on this?
How do these specific estimates of variance relate to the overall amount of variance in the sample?
The specific amount, they cover the overall amount of variance in the sample. And what we'll do is we'll add predictors and then we'll watch them shrink, right? So right now, there's the time and person error in here, and within person errors in here, and the between person error in starting place, differences in starting places here. Okay? So, what is it? What is the proportion of variance that is between person? So in step one, the main thing that we're doing is we're running the unconditional means model to partition the outcome variance to between versus within person variance, to think about how we want to fit or think about the subsequent substantive model, right? So, did I actually not advance the slide? Okay, so, or did I go backwards? I don't know what I did. Okay, so we've got the two pieces. The within person variance quantifies the between person variance quantifies the amount of variance between individuals regardless of time, right? 0.564. Where did we get that? We got that right here, okay? So the level 2 in initial status between person variance. And we've got the estimated within person variance, which quantifies the amount of variance within individuals over time. Okay? And that's 0.562. And where do we get that? We get this, the level 1 residual variance, 0.562. And that's how we calculate the proportion of between person variance. So the unconditional means model at this point is telling us that an estimated 50% of the total variance in alcohol use over ages 13 to 17 is attributable to differences between adolescents. Okay? So what about time? The next place we go is thinking about the role that time plays. So step 2 is the unconditional growth model, which is just adding the linear effect of time. Okay? So we're going back to our level 1 model, which we can see is exactly the same, except that it's got the slope coefficient for time. Right? The error term is the same, although it should be different in the output. And then we see that the level 2 model has changed because we're now not only predicting the randomly varying intercept, but we're predicting the randomly varying slopes. Okay? And then here's our composite model that has the 2 structural components and then the composite error components. Okay? So error between persons, error in intercepts between persons, error in slopes between persons, and error within, leftover error within person. Okay? Does that make sense? Am I belaboring it? Okay. Okay, so here's our intercept right here. So the fixed effects result for the intercept, the starting place here, right? And then here, okay, so this is just our fixed effects results. All right, so we're going to get to the variance components next. So we've got the intercept starting place, and then we've got the slope coefficient for time, right? So what does it tell us? It tells us that adolescent alcohol use over 13 to 17 is predicted by the starting place of 0.651 plus an incremental growth in alcohol use per 1 unit of time. So 13, 14, 15, 16, 17. Okay? Just like regression. Make sense?
So it could be that the intercept is not significant, so maybe everybody starts out at the same place, but then the rate is different for each person?
It could be, but I don't know, like if other disciplines where it might be more expected that the intercept wouldn't predict the outcome. I'm used to seeing the intercept being significant. Do other people have thoughts on that question? Like, when is the intercept not significant? It is sometimes not significant.
Well, there are several components of the intercept that can be significant. Like the intercept itself can either capture significant variance of the sample or be significantly different from zero. Those are two different things.
Mhm.
And each can, I guess, potentially relate to the outcome as well.
Mhm.
Yeah, I think that's as much about scaling of your measures as anything else. So if your intercept just happens to be around zero because of the combination of the scaling of your instrument and the pattern of change, in this case, the x-axis is time, and it happens to be zero, your intercept's going to be non-significant. But other than that, in some cases, I think the way, in Chris Kaler's example, I think the way the data were coded, the intercept actually has some meaning. In most cases, it's somewhat arbitrary. And I think it all depends on the degree to which the sort of numeric properties of your scale would indicate that at your first time point, the intercept should be zero under certain conditions, and whether deviance from zero is meaningful. So, and that might relate to individual subject variance.
So in terms of the variance components, we've added them. We've added terms for that. So we've got our within-person variance here, which has shrunk, right? There's still statistically significant within-person variability, but there's less of it because before it was
0.5 something?
0.5. Yeah, they were both 0.5, but yes, that's true. 0.562. And then the level 2 variance in intercepts, in rate of change, and then the covariance between intercepts and slopes. Okay? So what is this telling us? That we have shrunk, we have done a better job at modeling within-person change by adding a linear effect of time. We have done that. There is still between-person residual variance in initial status and in rate of change, right? Both of these terms are statistically significant. And that the estimated residual covariance between initial status and rate of change is non-significant here. Okay? So that's what all that information is telling us about the model. What's the bottom line? The bottom line is that adding time was good. We probably still need to add more predictors. Let's see. Okay, so this is the pseudo R squared, and so this is another way to just think about how our model has changed due to the addition of different predictors. So at this point, the one that we would be talking about is the one for the level 1, the movement from the unconditional means model to the unconditional growth model, right? And so we can calculate an estimate of variance explained by adding the term for time, okay? In these two examples, we're talking about moving from the unconditional growth model to the subsequent growth model. So we can talk about calculating these pseudo R squared estimates next week when we start moving into adding substantive predictors. The idea is the same. So that's just another way to kind of crunch the numbers and think about how you're changing the data. So in our example, what we have is a 40% of the within-person variation in alcohol use is associated with linear time. And so we got that by taking the initial within-person residual variance minus the subsequent, once we added time, divided by the initial within-person variance. Okay? So it's the same idea over and over again. It's just calculating different proportions based on the L. Any questions? Does that? Yeah, all right, good, thumbs up. All right, so what's the story? The story is about half the total variation in alcohol use over adolescence is attributable to differences among teens, between teens. About 40% of the within-teen variation in alcohol use is explained by linear time, so we did a decent job there. There is significant variation in both initial status and rate of change left over in the model. So that means that we need to think about exploring other substantive predictors to try and further reduce those residual variance components. And surprisingly, teen initial status and alcohol use here is not associated with the rate of growth in their alcohol use. So that's the association between the intercept and the slope. Okay? That's what we just found out. All right, so now we're just gonna kind of walk through the same thing, except that we're gonna do it with the smoking trial. So we saw this last week. These are the descriptives for the SPOMS, which SPOMS is, I think it's square root of profile of mood states. Okay, so basically what this is negative mood. That's what we're tracking as a dependent variable measured at baseline, session 5, which is actually when they were told to quit smoking cigarettes, session 6, session 7, session 8. Last week we did look at the numbers and look at how, when we were just thinking about, is this going to look like a linear change model? And we thought, maybe not, because we see this peak here in negative mood at session 5. Right, so we can add a linear effect of time, but chances are that's not going to be, we're going to have to try other things. This is just more information about the study. So the data set is 179 subjects, smoking cessation study. Scale is 1 to 5, but it is square root transformed. Okay, I just settled that. So we start with the unconditional means model, which is the same thing we saw before. But now instead we're going to look at the code. Okay, so we got the equation, and here's the code that's going to test it, and this is in SAS. I always start with SAS. That's where I'm most comfortable in terms of MLM. The SAS and the SPSS code are actually pretty intuitively similar, though. So what are we going to do? We're going to run proc mixed. We're going to use the data set called POMS. We're going to run full information, maximum likelihood, estimation. We're going to ask for the variance and covariance parameters. So this is level 1 data, level 1 variance data that we use to calculate those ICCs and so forth. This information here is just sample selection information. It's saying, let's see, what does it say? Okay, so no, and you need more than one valid observation on the dependent variable. Time is greater than or equal to 0, and the first data point is not missing. And then this is what is that variable? There's no missing data for yes, no, abstinent for week 1 and 2. So it's just selecting a subsample with certain missing data characteristics. So here's our level 1 model, here's our level 2 model. So for our level 1 model, it says we have the random statement and we just ask for the intercept, right? Unconditional means model. This is our type of covariance matrix, so unstructured, and then subject is ID number. In the level 2 model, we have ID number in the class statement. It's basically saying like, what's the nest? And the model, here's the level 2 model statement, which is model mood, so mood is the DV, equals, and then there's nothing. But there is something, there is the intercept is here, it's just that it comes as default. Okay, so there's a a ghost of an intercept term right here. Make sense? Yeah? Okay. Here's the key in case things don't make sense. So what's the information? So this is SAS output, right? And the first thing we're looking at is the variance components, right? So we've got the between person residual variance and the within person residual variance. And then here's our fixed effects estimate. Here's our intercept, okay? So at this point, our substantive piece of information of interest is what is the intercept, right? And then what are the two variance components? So if we go back to, actually I'll go back to it in a second. So first let's calculate the proportion of between person variability, which in this case is 54.1%, right? Which we just took from taking from these two numbers, okay? And so then this is just going back to the unconditional means model and plugging in the numbers, right? So predicted POMs over J sessions, we have like 5 sessions, is equal to the intercept plus the 2 error terms, the between and within person error terms in the unconditional means model. Okay? So you guys know where I got all that from the output. All right, good. So now we're just going to add the effective time. So the only place that this is different is that we now do have the term for we now are adding the linear effective time here. And then on the random, the statement is intercept is the same, but then we're also adding in time. Everything else is the same. Make sense? Mm-hmm. All right, good. So what happens? We can see that we've now expanded our number of error terms. Here's our residual within person variance, right? So what did we have before? Before we had 0.067. So we have explained some of the variance, right? We're now down to 0.053. And then we have our residual between person variance and intercepts, residual between person variance and slopes. Here's our intercept term here. Here's the linear effective time. Okay? So, what do we see? We see the starting place for negative mood with a small reduction in negative mood over time. On average, we're treating it as a linear change. We know that we did have that bump, which is not getting picked up here, because on average, it did go down. And then we have our variance explained, which is about 25%. So the residual shrunk roughly 25%, indicating that about 25% of the variance was explained by adding the effective time. Okay, so less than the other example, but we might have a hint why, because we know that time is more quadratic in this example because of just that one initial bump in the quit date. Yes?
Could you just go over what the unstructured 1-1 and 2-1 and 2-2
Yes.
are one more time for me?
Yeah, so these are all the variance components, right? So here's our residual within person variance. So this is that EIJ, right? Here is our residual between person variance. So this is the difference in intercepts, right? And so this is the zeta 0I. And then this is the residual variance in rate of change. So it's residual variance in starting place and residual variance and rate of change. Both of which are significant, although this is not all that significant, but they're both significant. So it is still telling us that we have, things to explain, both in terms of intercept, but also in terms of how they're changing over the course of the study.
So the 2-1 is the covariance between the intercept and the slope?
Exactly. Yeah. So again, we see this like no non-significant covariance between starting place and rate of change. Yeah.
Is the variance explained by these variance components referred to as residual because the model is unconditional?
I don't know. I think of it as residual, just as leftover variance. But I like to think about things in very simple terms. So I think even with a conditional model, it's still going to say residual
Yeah,
here.
you're
It's
always
just
gonna have
think about it with
people.
regression, like the residuals. I
Yeah.
think that's how they're
Yeah.
using the term.
Yeah, this is just the ordinary residual that you get in any, this is just fancy regression stuff.
Yeah, it's just the residual broken up into components, basically broken up into separate parts. Other questions on this? So 1-1, just we're thinking intercepts. 2-2, we're thinking slopes. I's, we're thinking people. J's, we're thinking time points.
What does the UN or unstructured mean here?
I think that it's labeling the covariance matrix. It's saying it's unstructured. I'm assuming that if we changed it from unstructured, that there would be different letters here. Yeah, so it's saying under this structure, here's the information.
So if you have a different idea of how the data is going to be structured, would you do that here? Like if I think it's going to be, let's say, exchangeable right now, would I do exchangeable and then like test it to unstructured? Like how would you do that?
Yeah, I would.
Okay.
And I would see if it made a difference.
Okay.
So you would just change it
Mhm.
to here, change it here, and you could change it AR1, exchangeable, and I think there's like one other one. And I guess, I don't know if the answer would be more in the deviance statistics versus the variance components or both. I think you would have to just look and see
Okay.
how it improved, if it improved the situation and how.
I'm confused on random and fixed effects for a second.
Okay.
Here it's random intercept, but the solutions for fixed effects. Can we just clarify?
So the solutions for fixed effects, because, well, this is our random effects information, right? So the fixed effects is the intercept and time between persons, right? I think if we go back to the composite model. So we've got a between, this doesn't have the effect of time in it, but we've got two between person components, like structural components, meaning the intercepts, and then if we had time in here, the slopes. And that's our fixed effects information. That's our level 2 information. But it's level 2 information that incorporates level 1 information. If I where's the I don't have the composite model here, but you can see it better here, I guess. Does that make sense? Sort of. Do we have another taker on the explanation? Yes.
You're gonna only get the random piece of it if you're going to let, I think this is right, if you're gonna let that slope be then subsequently, you're gonna say, okay, now I'm gonna let the slope vary and predict it by the level 2 thing. Then you'll get a random effects result. Right now the intercept is allowed to vary randomly, but the slope is not. The slope is fixed because it is being held, assume that it's the same between all people.
Mm-hmm.
And so once you say, nope, it's random, it can vary between people, then you'll set it up differently and you'll predict it with usually the level 2 stuff.
And maybe it's a little confusing too, because like this is where we're just starting with these two things, but this is where we're going to see like treatment and things like that.
I also think of when both are fixed, that's like a regular ANOVA. And then when you add in the random effects, that's when you get into the strong growth modeling.
Yeah, when you get to the end of this, the answer to your question will become apparent. But what's fundamentally different about this approach to data analysis is that you're building models from the ground up, as opposed to testing a specified hypothesis from the top level back down, and then sometimes you back things out of typical ANOVA and regression models, but this is really you starting with, okay, if I assume nothing, what happens? If I assume that individual slopes matter, what happens? If I assume that level 1 covariates are important, what happens? If I assume level 2 covariates, and so on. Throughout the model, there are going to be significance tests that are less about the significance of parameters and more about what's the significance of having added, in some cases it's removing constraints from the model, added more components to the model. It's a different mindset.
I think it gets a little fuzzy in here because you've got these fixed effects, but these are two pieces of information that you're used to thinking about as a within-person effects. But this is incorporating both pieces of information, the within-person information and the between-person information. Any other questions? Okay. Okay, so this is just our summary. Level 2 structural model shows a significant negative effect of time with negative mood decreasing somewhat, right, by 0.5372 at each subsequent assessment. The residual has shrunk, meaning that the level 1 model is better at predicting individual responses due to the addition of time, and we calculated it as 25%. There is still residual significant variability in intercepts and slopes, and the intercepts and slopes are not significantly correlated. And initial status predicts average mood over time. Okay? Same type of summary as the last one. This is just plugging in the numbers, so predicted POMs over J sessions. Okay, so we've got our intercept, that small reduction due to time, and then the 3 variance components. Okay, so the 3 variance components being intercept, slope, and then that leftover residual. Okay, make sense? All plugged into the equation? Here and here? Any questions on that? I think that's kind of it, except that we're going to talk about syntax a little. Here's the SPSS example. So this isn't the unconditional means. This jumps straight to the unconditional growth model, but all you would have to do is drop this, and you would have the unconditional means model. Right? So it basically looks exactly the same. Right? Here's our random statement. In SPSS, it's got a fixed statement, right, with time on there, but the intercept is in there. It's just invisible. Cove type unstructured, subject ID number. And it's called mixed. So it's mood with time is the model statement, which is right here. Okay? Are there any questions on this?
If
Yeah.
you dropped the intercept from the random statement, would that then fix the intercept? Or did that have to be there?
There'd be no parameters in the model.
You could put no intercept in the fixed statement, but I'm not sure. Does anyone know?
I don't think it would run because you wouldn't have any predictors in the model.
If you only had
If you drop intercept anytime?
No, just intercept.
Oh.
So the intercept wouldn't be randomly varying. It would just
be fixed here. And why would you do that?
If people didn't individually vary at the intercept, but they were varying by their growth rates.
And that's like What's an example of that, like
Like
substantively?
everybody starts out in the same place, but they have.
But like
different
what, like in
races.
a type of study?
Oh, I have no idea.
Oh, I'm just, I'm curious. I'm
Because
curious.
everybody is a beginner
actually,
at something
you
or has
teach
no
something.
knowledge of something, and then you're teaching them
And I
stuff.
had
Right.
That's a good.
an example, I was helping somebody with a model like this, and it was with reading.
Mhm.
And her intercept was not significant,
Mhm.
but her growth variance was.
And so, and you thought to simplify matters, if it's not significant, why not just drop it?
Yeah, or fix it to. I don't
Yeah.
think it worked.
Uh-huh.
I wasn't running this up, I just said, oh, maybe we could try that. So now I'm wondering if it's even possible.
I mean, that's where the best things happen, is just by like adjusting one thing here, one thing there, and looking at how things change. You know, that's where you learn the most in terms of how, you know, the syntax maps onto the,
Right.
you know, what you're really trying to do.
Yeah, and I use M+, and so in my head, it's more straightforward on how to do that in M+. I was just wondering.
Yeah. So let's talk about M+, because I think there's some people in here that are probably more versed with M+ than I am. But I did try and pull together some analogous examples, and I had some help from Tim in terms of getting some latent growth curve examples. So in the course website, there are Tim's 3 programs for unconditional means, unconditional growth, and then full model with one predictor, right? And they're very well annotated and intuitive, so that's helpful. The difference that we kind of came to, though, is that those are latent growth curve models, and so they're run as a single model. It's not actually a multi-level model. And so what I did here is to keep things as sort of consistent across. I did an example of a multi-level model using M+. So this example here I pulled, I think, was 912. And so you've got, say, your title here, data. So here's the data set. The variables in the data set. Cluster, you can see the command here, cluster is ID number, right? What is the within person information? Well, it's mood over time. And then I sort of grade these out to show, like, okay, so then here's if we're adding a level 2 predictor, so it would say between is, say, treatment, for example. And then the analysis type says 2 level. And then here's your model statement. So you've got a model statement for within and a model statement for between, right? Where you've got intercepts and slopes, right? And then intercepts and slopes within, intercepts and slopes between, and then with the addition of a treatment variable, you would have the intercepts and slopes between regressed on treatment. So that was an example that I could come up with that looks the most similar to this SAS and SPSS. And then I also found this one, which is 916, and this is where they do a data flip. So you still have your title, carried out as a 2-level growth model with a data wide to long command. So I just wanted to show you the flip syntax. You've got your time varying outcome, time varying predictor turned into single variables the same way you would if you were flipping from wide to long in other programs. And then it just looks a little bit more familiar because you've got here ID, you know, you can think ID numb here. The repetition is time. Here are your variables. Use these variables. So we've got 2 static covariates, time varying outcome, time varying predictor, ID, and time. And then you can see cluster is person, within is time and that one time varying predictor, between is these 2 static covariates, analysis type 2-level random. And then here's your model statement here. I mean, I think when you flip back and forth between these two, you can get the logic and track the logic to the other syntax if interested. I don't know if you guys those who use M plus want to add anything in terms of like sort of talking through the logic of the code on either example. You want to do this one or the other one?
This one.
Okay.
I think there's information about time that we're not using here, about like the relative distance between parameters, between estimates for the slope that we're not using.
There's a parentheses after each of the.
I think this would be, right, so this is throwing away, this code is throwing away the fact that it's 1, 5, 6, 7, 8. And it's treating it as 0, 1, 2. It's treating it as a categorical variable rather than a continuous variable. So what would it look like to put that time in?
I think after each indicator you add at and then the relative distance. So at 1, at 5, at 6, at 7, at 8. Because right now those are just the variable names.
Okay, so this would be at 0.
Yeah.
This would be at 5.
4.
4, and then 1, 1, 1, like that?
No, then
No,
4,
5,
5,
6,
6,
7.
7.
Oh, okay, because it,
Yeah,
okay.
You
the
map out
at,
the trajectory.
correct, the at syntax in M plus essentially defines a starting value.
Okay,
So that's how the distance is indicated in those kinds of statements.
Yeah, I think if you use this syntax, it would freely estimate the relative contributions of the indicators to the slope.
without taking into account the different distances between them.
But without taking into account the known information about the distances between those variables.
But if this was 0, 1 month, 2 month, 3 month, 4 month, would it not matter?
It depends on
If
whether
they're
you want
equally
to have the...
spaced.
Yeah, like if they
Or
were,
No, I think you want to specify that they're equally spaced somehow. And then if you have freely, if you have varying time measures, I think you can go into that next week. There's a different way of specifying what the sort of varying time indicator is,
Mhm. Okay.
which I forget off the top of my head.
I think you just put an asterisk, don't you?
Asterisk is a starting value.
Yeah,
At asterisk. And then it would determine.
yeah.
Oh, yeah.
Like it would freely determine.
Yeah.
Yeah, the other thing you do is you email support@statmodel.com and it tells you.
if your license is up to date.
No, even if it's not.
Oh, really? I thought they would
Or you
talk to
Google
you.
it and like it's like
Yeah.
inevitably it's
Yeah, then you
online.
Google it, yeah,
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 and there's such good M plus documentation.
yeah,
The manual itself is really
And
good.
then you get emails.
yeah.
Yeah, I just pulled these. I pulled
It's a great book.
this one straight from the documentation, and then this one I pulled from the documentation, but I just plugged in the Kaler example variables instead, just so it would look more similar to the other two examples. Are there other thoughts or questions? That's all I have. Whoa. All right. Well, email me, and if you have tips like on the M plus type stuff of like how to, like to do multi-level modeling in M plus. And then I guess we didn't talk about actually. Wait, can we talk about this 1 second? So the fact that M plus runs a latent growth curve model as one level. What is the difference between a latent growth curve and randomly varying intercepts and slopes?
They're
Like,
modeled
is-
as latent variables.
There's no
I don't think
difference.
there's a difference except, well, you have to include the fact that you can also regress on the indicators separately from the growth model. And I think that would be the actual equivalent of regressing on between subjects variation.
Okay. But like just sort of mathematically, random effects, latent variable, can
Well-
we interchange them?
Yes, as long as they're random effects, I think, because then there's variance, whereas if they're fixed effects, then it's random variance attributed to that specific fixed effects component.
Uh-huh.
Yeah, I think the specifics of the estimation techniques that M+ uses and SAS uses are slightly different, but conceptually come from the same place.
Okay.
What M+ is always trying to do is build more and more complicated models.
Uh-huh.
So M+ is going to internally maintain the individualized growth parameters so that you can use them to predict other things. So, look, for example, look at two simultaneous growth models, et cetera. With SAS, you have to kind of build that yourself, do the first model, get the parameters,
Spit 'em out.
and then do something with a second model.
Okay.
M+ is designed to make that all straightforward for users who don't understand the mathematics to do it well.
Okay. All right, that's very helpful, because I definitely was like, what's the difference here? Okay.
One suggestion that I'd have if you're trying M+ and you're not used to working with data in it, though, is I would not flip your data in M+, just because it's really hard to look at it and know if you did it right, because it's all in unlabeled, like,
Right.
morass of
Right,
numbers.
it's
So
just numbers.
I usually do it in like SPSS or something, get my
Yeah,
data
don't
set
do
to
any
go,
data management
and then
in
put it in M+.
Yeah.
Yeah.
Like, don't do that.
Yeah, that's good point.
You'd be like, maybe it's right. I don't know.
Yeah.
So,
Well, you have no
Well, I
way to
guess if
look
you
at
had
it
like just
in
like,
M+.
not a lot of variables and cases, but yeah.
Yeah, the problem with M+, you just can't look at your data.
Right.
You put it in, and it's in there, but there's no way of examining your data the way you can in a typical stats program.
Right. Right.